Hello, my name is Tom Gregory, and I'm a product manager at Future Facilities for Six Sigma ET, our thermal simulation software for the electronics industry. Today, I'll be talking about why thermal simulation is a must for electronics design. So, electronics, as we all know, is getting ever more complicated, and there's so many things to consider. We've got increased power density, high frequency signals, high number of layered boards, hundreds of components, thousands of nets. Things are getting ever more complicated, and there's so many things to consider when designing modern electronics, from signal integrity, power integrity, design for manufacture, design for tests, cost, weight, size, etc. So there's so many things to consider, and one really important one is thermal. And it can often get forgotten about in the design process. But why is thermal design so critical when designing electronics? Well, three main reasons. One is performance. Will the product work correctly to the temperature it's operating at? If the temperature is too high, the device may just not run. Or fail, or it may run at lower performance. The other important reason is reliability. So the device may work fine in year one, but if it's running too hot, then it may fail prematurely. And also safety is really important as well. Like, we don't want particularly consumer electronic devices to be too hot to touch. And worst case scenario, if a device is too hot, it might cause a risk of fire. So it's really important to consider thermal design when designing electronic products for those three reasons. And we did a survey of engineers in the electronics industry and found that reliability is their top sort of design priority. And as I said before, thermal management and reliability are interlinked. If a device is too hot, then it can lead to reliability issues down the road. And engineers also said they need to spend more time on thermal management, on designing thermal management throughout the process. And one of the other really important things we found in the survey is that over a quarter of people wait until after a design has been completed before they consider testing for thermal issues. So one of the things I was talking about in this presentation is how simulation can be used to do thermal design earlier in the design process and validate your thermal design earlier in the design process. And as I said, overheating electronics can cause reliability issues. Almost every engineer we surveyed said that they've had projects derailed by late stage complications, and 1 in 5 of those late design complications was caused by thermal issues. And it's worth remembering that a design failure found really late in the design process can be really costly. So it can be £20,000, it could be £200,000, it could be more. The knock-on costs can be huge if an issue is found late in the design process. So one of the things we surveyed is, when do engineers test the thermal management of their design currently? So about a quarter do it early in the design process, about 50% do after the first prototype, and 27% do after design is complete. And one of the things that's important to note is that the later in the design process it is, the more expensive and the more time consuming it is to rectify a design issue, particularly with the thermal design of your electronics device. So Rod from Lascar Electronics sort of emphasised this. He says that tools that enable design checking should be deployed at the earliest stage. Each remake can cost thousands, but even with the cost of remaking is minimised to a few £100s, the biggest issue is time loss. If your engineers waste time fixing a late stage issue, or you're late to the market, that can be hugely costly. And here's another quote from one of the customers, Sackett from Facebook. given how the electronics industry is changing, we now have to start modeling simulation at least 3 to 4 years in advance. So Facebook are using thermal simulation to make sure that their thermal designs are ready for whatever comes in the future. And again, another quote from Facebook, thinking about the pressures on engineers. Everyone thinks at lower cost with high reliability, which is obviously really challenging. So it puts the pressure on design engineers to find good solutions, and being able to use thermal simulation early on, it makes this process a lot easier. So as I mentioned before, thermal simulation can help you identify thermal issues early in the design process. But first of all, what is thermal simulation? So thermal simulation allows you to create a digital twin of a real product or design, and it uses a technique called computational fluid dynamics to predict the temperature and airflow through the device. So below we've got a image of a thermal simulation of a VR headset, and on the right is a picture of the real thing. And thermal simulation can predict all 3 modes of heat transfer. So conduction, which is heat transfer into moving air or fluid. Convection, moving into moving air or fluid. Conduction, which is heat transfer into a solid, and also radiation, so heat transfer using through the radiation. So we can model all those 3 factors, which, depending on your design, will be important to ensure that your device does not overheat. Thermal simulation can also do transient analysis, can model liquid cooling, can model the impact of solar radiation, so things getting warm when in the sun, and also can model the impact of joule heating, which is the heating joule to the current flow through traces or cables. So what we're proposing is that before simulation, or people that don't use simulation, they have to make designs based on sort of best practices, and then they go and create a prototype, and then put it in an environment chamber, measure and test that design. And if it overheats, you've got to go back around and fix the issues and then redo your design, which can be quite costly. So what we're recommending is you do your electronic system design with simulation, which means that you can test your thermal design in simulation, test that the device will operate at whatever operating conditions you want, say 50 degrees C, and then when you go to create a prototype, measure and test, you're much less likely to have any thermal issues that come up. So what thermal simulation allows you to do is it gives you a visual representation of the temperature and airflow in the device to quickly highlight issues, which are sort of impossible to get that visualization typically with measurements, and enables you to do that early, so before a physical prototype is created, and identify those issues. And if you do find issues, you can experiment with solutions without having to do physical prototyping. So you can, add a heatsink or add an extra fan really quickly in simulation. You don't have to wait for parts to arrive or a prototype to be built. You can do it really quickly in simulation. So that's why people are using thermal simulation tools. So I'm not going to go through these all, but there's many different design questions that thermal simulation can answer. It can answer questions on, electronic component placement on a PCB, what package types do I use, the design of the copper pores on layers, is a heatsink required, do you have to add thermal vias, it can advise on how the enclosure needs to be designed, and if fans and what other airflow needs to be provided to cool the component. So it can answer many questions that might come up during the design process. So we've talked about how thermal simulation can help, but what do engineers want from a thermal simulation tool? So again, we did a survey of engineers, and found that the most important thing they want from simulation tool is accurate results and really clear results analysis, as well as fast solve times and automated processes. So we've really worked hard to make our thermal simulation tool Six Sigma ET match the needs of engineers. I think some engineers have got maybe used thermal simulation tools in the past and found too difficult to use or couldn't get the right results, or maybe they've just got a perception from perception that it's just too difficult. It's not the right tool for them. And I think what I'm trying to show you today is that modern thermal simulation tools like Six Sigma ET really can be really easy to use, and you can really get the data you need to make better design decisions. So yeah, this is reflected in our survey that many engineers consider thermal simulation to be too complex or too time consuming. So that should be our real focus when developing Six Sigma ET, to make sure it's really easy to use and also really quick to model, do the simulations, and also to analyze the results as well. And it's there's a bunch of thermal simulation tools on the market. It's really important that you take a look at modern tools like Six Sigma ET because we've got new capabilities, much easier to use and faster performance that the other tools on the market don't necessarily have. So let's dive into a little bit more detail about Six Sigma ET. So Six Sigma ET is, as I said, a thermal simulation software for the electronics industry. But we do a wide range of applications across the electronics industry, from modeling the insides of semiconductor devices right up to modeling a rack with dozens of PCBs and thousands of components. So I'll talk through some of the examples on this page. So we've got an LED light bulb on the top left-hand corner, which we've modeled, and you can see that it's been modeled using CAD data from mechanical CAD tools. Got a picture of an electrical server next there, which has been built entirely using Six Sigma ET. So in Six Sigma ET, we can build up models using our intelligent modeling object, which means you can build models before mechanical or electronic CAD data has been created. Some other tools require CAD data to be generated first. And the third image is a camera. You can see the level of complexity of CAD that we can model, and same with the image on the top right, which is a robotic arm. Some simulation tools in the past really struggled with angles or curved geometry, and that's one thing we've really focused on Six Sigma ET, is to ensure that we can simulate really complex curved geometry. The bottom left is a semiconductor device, and we can model down to features as small as 1 micron when modeling detailed components. And liquid cooling is becoming more and more important. So you can see a picture of a power electronics device which is liquid cooled, which we can model using Six Sigma ET. And as I said, we can also model racks with a huge number of scale, thousands of different parts in a rack model there. And we can also model things in particular environments. So on the bottom right corner is a piece of electronic equipment for a mobile phone base station, and that's modelled in outdoor environment, and we can consider the impact of wind, the temperature, and also the heating during solar heating. So it's much easier to, in simulation, represent these high temperatures, environments. Although it is possible to do it in environmental chambers, it's much easier to do it in film simulation. So we work with many different companies across the electronics industry. Here's just a selection. So we work it with companies in the automotive industry, such as Bosch, Draxmeyer, and Bros, and work with companies in the IT equipment like Facebook, Motorola, and Hive Solutions, Select, which is a defense company, and Roder and Schwartz, which I'm sure many people are familiar with, make oscilloscopes and other test equipment. I'll talk a little bit more about Roder and Schwartz later, and Qualcomm, who make devices for many of the devices you'll be using, like tablets and mobile phones. So we really are used across the electronics industry. So as I said, one of the reasons why people don't use simulation is because I think it's slow, and that might have been the case in the past, but Six Sigma has got a really powerful solver which can run CFD simulations really quickly. And we've also worked to optimize the model build, the solving, and the analysis. So this is a complex model built by Roder and Schwartz. And in some alternative software, it took them over 45 hours to do a simulation of this device, and they had to do it quite simplified in that tool. Whereas in Six Sigma ET, they were able to do the modeling, solving, and analysis in just 15 hours and do the full detail that you can see on the top right-hand corner. In many thermal simulation tools, you'll hear a lot about CAD preparation and CAD simplification and the importance of doing that. In Six Sigma ET, that is often not necessary, which means that instead of spending 20 hours on CAD import, you can just spend a few hours that's needed in Six Sigma ET, dramatically cutting out that time. Another process that could take quite a long time in some tools, which again puts people off, is gridding or meshing. You can see that used to take Roder and Schwartz over 12 hours, now only an hour in Six Sigma ET, significantly faster solving and also significantly faster analysis as well. So if your company is not doing film simulation because you think it will take up too much of your time and not worth the effort, then I just sort of consider you to sort of think again and maybe have a trial of Six Sigma ET to see if it meets your requirements. The other thing that's different about Six Sigma ET is it can handle the complexity of modern electronics. If you haven't used thermal simulation before, these figures might not mean anything to you. If you have used thermal simulation before, then I think you'll be impressed by this. We can model a huge number of grid cells, up to 750 million grid cells on the white hardware. We can solve 100 million cell model in an hour, again on the white hardware. We can solve tens of thousands of objects and cope with complex CAD and PCB designs. And you can see some of the detail there on the right hand side. So you've got a detailed printed circuit board there, and you can see that we model all the little components, traces, wires, etc. And then you can see that we've using the direct CAD geometry for the VR headset that's pictured there. So just talk a little bit more about the PCB modeling. So we can take PCB designs from Cadence, Mental Graphics, Zuken, Altium, Eagle, all the main tools, and import them using IDF, IDX, Gerber, ODB++, and actually IPC 2581 as well, and bring in a huge amount of data. One of the things I'd like to point out on this slide is that typically you will not have final PCB designs until really late in the design process. So I would not wait to do thermal simulation until you've got a final PCB design like this. I would encourage you to do what's on the left-hand side, which is to model printed circuit board simplified first with the rough component layer, component layout and the rough PCB outline and see if there's any problems with that first, which can then help guide the PCB design and make sure that that there's no late stage design complications. I'm sure anyone who's designed PCBs will know that you can't, it's not very easy to move a component from one side of the PCB to the other late in the design process. So with the PCB modeling, we can model we can import the board layout, the layer stack up, wires, traces, pads, PCB holes, reference designators, keep outs, and component location. These things are all really important to make sure we get the correct thermal data in and model everything that's important to make sure we correctly predict the temperature of the components. One that I like to highlight is vias. So vias are obviously plated holes that are used to connect traces between layers on the PCB, but they're also really important for thermal, as you can they can also act to improve the conduction from the top and bottom of the PCB and get the heat through the PCB and away from sensitive components. So it can be really useful for improving the heat transfer away from components as well. So another thing that's really important when doing thermal simulation is ensuring that you have a really good component model of the electronics devices that you're using, particularly components on your printed circuit board that are either high powered, so have a big impact on temperature, or are very thermally sensitive, or both. I mean, typically the high powered devices are quite thermally sensitive as well. And it's really important that you get a good representation of the component and their thermal properties. And it's important to work with component manufacturers to get the most accurate thermal model you can get of the device you're using. So we have 4 different ways of modeling components in Six Sigma ET. One is the simplified block, which we use if there's no other information available, and it's just a very, very rough approximation of an electronic component and the heat transfer away from it. And the other model of components we use is called 2R, where you specify the thermal resistance between the junction of the component and the board, and also between the junction of the component and the top of the component. You can typically find 2R resistor model data on data sheets, but it isn't the most detailed or accurate method of modeling components. So I'd really recommend, particularly for high-powered components, to get in touch with your component manufacturer and ask for either a compact Delphi model, which is a resistor network which represents how heat transfers away from components, or ask them for a detailed model to represent the heat transfer away from the component. So we work with many different companies like Intel and Xilinx and others to make sure you can access thermal models that can be used in Six Sigma ET. So one of the things that's important about Six Sigma ET is trying to automate things as much as possible. So if you've done thermal simulation or other CFD before, you know that meshing or gridding is a really important part. It can be quite difficult and time consuming. When Six Sigma ET, we've made that process automated, so it's much quicker to do the thermal simulation process. We've also got automatic error detection and also automatic reporting, which is tailored to the needs of electronic design engineers. So we're not a general purpose tool, we're specifically done for electronics, so every result we can give you is tailored towards the needs of the electronics industry. So as I mentioned earlier, thermal simulation can give you really sort of unique insights into the heat transfer and the airflow. So this is a model of a server, actually Backblaze server, which is an open source storage server. And you can see we've got these what we call streamlines, which are a visualization of the airflow of the system. And this is colored by temperature. You can see the temperature rising as it goes through the system. So this is just something that would not be possible. It's very difficult to do measurements. You can try doing it with sort of smoke or whatever, but it's very difficult to do measurements, whereas in CFD it's really easy to visualize the airflow or fluid flow through the system. So this is some results of PCB simulation. So you can see this is actually an Arduino board. So you can see we've imported the detailed PCB data, added powers, and then you can see how hot the PCB is and how hot the components are on the board as well. The other thing mentioned earlier in the presentation is dual heating. So this is the modeling of electronic current and the heating through to this. This is a bunch of cables connected to a bus bar, and you can see how hot the bus bar gets when I suspect hundreds of amps are being passed through this device to make sure that doesn't get too hot. So power distribution is important, but also power electronics, like using electric vehicles, industrial systems, rail, aerospace, etc., get quite high currents. So you need to make sure that those high currents are not generating too much heat. So one of the things that comes up and has come up in our survey is thermal simulation accurate? Well, yeah, obviously this is something we're really focused on, and we validate 6 Sigma T against a wide range of analytical solutions and published data. And our customers also very regularly compare simulation results with measured data as well. So on the right, we've got a comparison between experimental and CFD done by UTA, a university in America, on a compute server. Again, so really great match between simulation and experimental data. And the image on the left, well, from the left, is a comparison between experiment and simulation, very close, of a detailed component done by Thales. So really accurate tools. You do obviously, of course, need to make sure that your input data is accurate. If you don't put accurate data in, you won't get accurate simulation. But if you're able to get accurate data and focus on getting the most accurate data for the bits that are most important in the thermal simulation, you get really accurate results you can rely on to make design decisions. So just a quick note for people who are already thermal simulation users and might use IcePack or Flowtherm. We know that having access to your old models is important. So you can now transfer models from IcePack and Flowtherm to 6 Sigma UT via the ECXML mutable file format, which means transitioning 6 Sigma UT is a much easier process. So that sort of concludes today's presentation. So we've discussed why thermal design is really important when designing electronics, and why it's really important to consider thermal design really important really early in the design process, and how thermal simulation can help you identify thermal issues much earlier in the design process and experiment with different solutions earlier on. And we've also discussed how we've tailored 6 Sigma UT to match the needs of electronic engineers and their requirements for simulation, and developed a tool which is easy to use, fast, and can give really clear results. to help guide your electronics thermal design. So yeah, that concludes the presentation. So now sort of open it up to any questions that you might have. So we've got one question coming in about how do I get thermal models from my supplier of electronic components. So the important thing to know is that typically thermal models are somewhat confidential and are only given to customers of a given chip. So it's important to get in touch with your representative and ask them for these thermal models, and we can import thermal models using the Delphi, which is a visitor network model just talked about earlier, and also detailed thermal models as well, which can be also transferred using the ECXML4 file format. So it doesn't matter what thermal simulation tool your manufacturer uses, we can still transfer that data into Six Sigma. Okay. Well, I'll leave it there. So thanks everyone for your time. Please sort of get in touch with us if you'd like to learn more about Six Sigma UT, and if you'd like to take a 30-day trial of our software. We're also happy to discuss with you whatever thermal challenge you have at your company and discuss sort of how we can help. Yeah, thanks everyone for your time.